second lecture of mine in this ESA course. This time, this presentation, this lecture, actually, rather than a lecture, it's actually more a presentation. It's like a talk. It's not so much technical, let's say. The topic is DTE Hydrology and landslide risk. DTE stands for Digital Twin Earth Hydrology, which is an activity, but actually is a project. Actually, are two projects, or better saying, two phases of the same project. And the aim, as we will see, was and actually is to reproduce a digital replica of the Earth system, in this case for the water cycle. Then there is also a bit of focus on the landslide risk. We will see how in this project it's possible to develop a tool to basically reproduce the water cycle of our Earth, and then there is also an application of the data used for building the system in landslide risk. You may have understood from yesterday that I'm actually not an expert on landslide, but after this lecture there are for sure real experts in landslides. But I show you here what we did as a case study under this context. So an overview of what we will see, as I already said, the objective is to present the DTE Hydrology project, whose aim is to create a digital replica of the Earth system for the water cycle. So we will go through the evolution and the process of this activity. First implementation we have carried out in the Po Valley with several case studies. We will see in the following slides what case studies means in this context. And we will do a focus on the landslide risk assessment. Then there is the second step, because as I already told you, this project are actually two projects, the DTE Hydrology and the evolution, in which we have basically extended what we did in the first prototype to the full Mediterranean basin, with applications linked to what-if scenarios. We will also define what a what-if scenario is within the digital twin of the water cycle in this case. And then there are the conclusions and the outlook. So the DTE Hydrology and DTE Hydrology Evolution project, as we said, it's a project, it's an activity aimed at create a digital twin Earth for water cycle, so for hydrology. Based on the novel high-resolution Earth observation data, and able to predict hydrological extremes and to help application, let's say, aimed at the water resources management. Of course, they are ESA projects that they are led from CNR-IRPI with several partners in the consortium. An interesting to me is that the project has recently come to an end, the evolution part also, and the final report is freely available. There is the QR code to be scanned if you are interested. However, the report in PDF is in Zenodo, so if you want more details on what you will see today in this lecture, you can just check it out. So the concept, of course, is the same for DTE Hydrology or its evolution phase, no? Because it's actually a matter of scale. But the concept of a digital twin for hydrology, for the water cycle, is made of three main components, three main ingredients, let's say. There is the data cube, based on Earth observation and also in situ dataset. So basically there is the data. Here, the important thing is that we are looking at high-resolution datasets, so decision-making scale. Also because the final aim of the tool is to make somehow predictions, to be applied in water resources management, for instance. So we are talking about 1 kilometer spatial resolution and less than 1 day, or as a maximum 1 day temporal resolution. Another important essential component is the modeling platform, which has to serve as a support of the data, and also in vice versa. Should be able to integrate such data, so should be able to integrate high resolution data, because as you know, when doing modeling now, when you have to work at different scales, it's not just a matter of upscaling or downscaling. If you want to work at a target scale, you need a model that is able to reproduce the physical processes occurring at that scale. So we need models that are able to properly integrate and actually use the high resolution Earth observation data sets. Then there is another essential component of the system, which is the cloud-based platform, which has to be able to integrate both other ingredients, so the data sets and the modeling, that can be used to model, to visualize the data for processing, and so on. Then there are some additional components that are needed, as for instance the computational infrastructure, because it's, as you can imagine, we are talking about large amounts of data now when we talk about high resolution spatial and temporal resolution data. There is the community that is super important, because has to be engaged with these activities, because actually all these tools that we are developing has to be used now somehow. So the community is super important. Just a few words saying that these activities basically fits perfectly within the Destination Earth initiative, which is from the European Commission with as a partner in CNWF, ESA, and the EUMETSAT. And whose aim is actually to reproduce a digital twin of Earth. No? So all the systems, all the components of the Earth system, among which there is hydrology, water cycle, that is in this case our target. So as we understood here, the concept, the objective is to create a prototype, a digital twin of the Earth system for the water cycle. We have also a paper summarizing the objectives, what has been done, the requirements, and the status of the art, let's say, in this sense. Still talking for the digital twin for the water cycle, of course. That is under review. I hope that will be published soon. However, the main requirements are the need for high spatiotemporal resolution data, so high spatiotemporal resolution of observations. As I said, decision-making scale, so 1 kilometer and 1 day as a maximum. This is useful for both calibration and validation purposes. And also there is the need, as we already saw yesterday in the presentation about irrigation, there is the need to represent human activities, because at this scale often they are not negligible. In this slide there is also the new version of the water cycle provided by ESA that yesterday I anticipated you when talking about irrigation. So how can we meet these requirements? Well, still the answer is remote sensing, because the remote sensing technology allows us currently to have this high resolution data and then to track human activities as well as processes, let's say, occurring on the Earth's surface. So high resolution data, we are actually in a new era for hydrology. Also, this topic has been somehow anticipated yesterday, but you may be aware that currently we have high resolution, talking about 1 kilometer, and now when I talk about high resolution, we have soil moisture data. As for instance, on the left side there is an animation of Sentinel-1 data over Italy, in this case retrieved by the RT1 algorithm developed at TUVN. It is clear how you can catch the high resolution features now with this kind of data sets. In analogous way, we have high resolution precipitation. There are here in this slide animation showing products developed within this project, within DTE Hydrology. We have high resolution evapotranspiration. The evapotranspiration animation shows the same product, which is GLIM, developed at UGent at the coarse resolution 25 kilometers. That is the original dataset, let's say, and the new version at 1 kilometer developed within this project and also other ESA projects, as we will see in the following slides. Then now we have irrigation water use datasets, but we already talked about this. So basically the message here is that up to a few years ago, very few years ago, we only had coarse resolution data for main hydrological variables. But now we have satellite observations at high spatial temporal resolution that allows us to build tools like the one I will present in this lecture. High resolution, okay, again, is actually a new research trend. Just considering last year, if you read some literature about several high resolution, long-term and gap-free soil moisture datasets have been recently published. They are really a lot. The same applies for air temperature, evaporation, precipitation. So currently there are really a lot of high resolution datasets for hydrology. Just a quick warning that we should always keep attention between the difference between resolution and sampling, which are pretty differences because several products out there are claimed to be at 1 kilometer resolution, for instance, but there are some that are at 1 kilometer sampled at 1 kilometer, which is not actually the resolution of the information. Here, just as an example, I'm showing soil moisture anomalies for April 2020 over the whole Italy. So basically the same information. One dataset refers to a real high-resolution product, another one probably not. Of course, I will not say which products and which product is really high resolution and which not. But it's clear that in the map now on the left side, you can clearly see the high resolution features, while in the other one, yes, the product is sampled at 1 kilometer. So we have one data each 1 kilometer pixel, but actually the information is at a coarser scale. But okay, coming to the DTE Hydrology project, so the first implementation, the first prototype, as I said, the first implementation was carried out over the Po Valley in northern Italy. Why this area? Well, for different reasons. First, the Po is the longest Italian river. The basin is a data-rich basin for several hydrological variables and data sets, and also is strongly human-altered, because there are a lot of dams. It's the widest agricultural area of Italy, and so on. Here, when we developed this prototype for the Po Valley, we already had all the components of a digital twin for hydrology. We had our data cube with rainfall, soil moisture, and evapotranspiration, the three maps on the top of the slide. As you can see, we had the platform, a cloud-based visualization tool. And also, we had an hydrological model able to integrate this data. More in detail is the continuum model from CIMA Research Foundation, which is the partner whose aim is to provide actually the modeling part. And from this hydrological model, we have three modules that allows us basically to show through three case studies what we can do with this kind of tools actually. So once we have developed this digital twin of the hydrological cycle, what can we do with this? And so we have a case study about flood, one about irrigation, and one about landslide. I will not spend so many words on the one on flood, also because this afternoon we have the practical session, which is for irrigation, but as anticipated yesterday, I would like to save 20 or 30 minutes for playing a bit with the new version of the platform we have developed, and we can go into details about flood. There is, for instance, a a bidimensional simulation, hydraulic simulation of the flood occurred in Sicily, Italy, southern Italy, last October before the the Apollo Medicane. So it's pretty interesting and also impressive to see that flood. I will spend now just a few words on the irrigation part and on the landslide, as anticipated, as a case studies of this activity. Before continuing, there is a video that probably explains much better than me the concept of a digital twin for hydrology. So this was developed for the first prototype over the Po Valley. We have the Po Valley, we have the data sets, soil moisture, both from satellite and model, just to see that satellites has gaps, spatial and temporal gaps that models can overcome. There is evapotranspiration, precipitation, and all these layers are stored in what we call data cube, 4 dimensions, because it's space-time, 3 dimensions, and then several variables. We can couple these data sets with hydrological models to estimate, for instance, river discharge. And now the video will also show how can we use the data cube in case studies linked basically to water resources management or to prediction of hazards, actually. This is the module for landslide, where we have mapped the landslide risk based on soil moisture and rainfall data, and we will see this into details in a few minutes. So here there are some actually occurred landslides that match with the risk we have highlighted. There is the irrigation module, where basically with the soil moisture based inversion approach we saw yesterday, we are able to map irrigation, water use. Here there is another case linked to flood. It's a simulation of the flood occurred in the Enza River in December 2017. And okay, this is just the end of the video. I think we have understood what we are talking about. 1 kilometer, 1 hour, so decision-making scale. So, the irrigation water use mapping and quantification, I will be short here because basically the method is the soil moisture based inversion approach that we have thoroughly explained yesterday. Here we have implemented the method with data sets from the DTE Hydrology project, so from the data cube basically, and we have selected an area located close to Reggio Emilia. The period is 2018. We also had some benchmark information on irrigation occurrence here. Actually, not so reliable because refers to a group of scattered fields, not the maximum of life, but still is data, so somewhat valuable. And with the soil moisture based inversion approach, and through the data cube inside the DTE hydrology, the digital twin for hydrology, basically, we have calculated the cumulated irrigation amounts for the season 2018, highlighting more irrigation on the east side with respect to the west side, which is comforting because by talking with local experts, we know that actually the eastern portion is much more irrigated than the western one. We also validated a bit with the data we had, highlighting that we are overestimating a bit irrigation, especially at the beginning of the season. But again, this is just to show that there is a connection also with in situ data, because the in situ data itself here is not so clear, let's say. However, here the message is not the performances in reproducing irrigation, but what can be done with this kind of tool. In analogous way, what can be done for landslides is the landslide risk mapping. I would like to thank here Luca Ciabatta, because this basically I'm presenting in this case his work. He is the expert of landslides at CNR-IRPI. what CNR-IRPI has implemented within DTE Hydrology for the landslide risk assessment? Well, we selected a catchment in the Oltrepo Pavese area. The catchment name is Ardivestra. During 2 different rainfall events, one in November 2019 and another one in February 2016, there were several landslides in this area, more than 100, and with different extensions, from very, very small ones to big ones. We have selected these events as a benchmark to test how can we predict landslide risk with the data cube inside the digital twin for hydrology. Before going into details, just a few words on the background of CNR-IRPI in the topic of landslide risk assessment. Basically, the activities of the institute is focused on the importance of soil moisture coupled with the rainfall information for the landslide hazard assessment. Why? Because soil moisture reduces the shear strength of soils, so there is an increasing landslide likelihood. No. On the right side of the slides, there are a few plots from a study of 2012. Those results are not so important, let's say, from a quantitative point of view, but just to understand the concept. Here, the team has developed the regression model to reproduce an actually occurred landslide, and several input parameters have been tested in the capability actually to predict the landslide, so to reproduce an actually occurred landslide. And basically, moving from the top to the bottom panel, what changes in the input model is at the beginning we were using only rainfall, and at the end a combination of several features of rainfall and soil moisture data, and you can see how the red and the green line are much more. There is much more matching with respect to the first panel. No, so the information here is that if we use also soil moisture together with rainfall information, we are able to better predict landslide risk. And this is the philosophy beyond the case study that has been implemented. As said, I will not go into details on the mathematics of the method, because actually is not my topic and probably is not so of interest in this context, but just a few words on the model that we have implemented here is that of Lu and Gott 2008, which is based on the hypothesis of indefinite slope. Basically, the analysis is focused on this factor. Fs is factor of stability, which is the ratio of mobilizing to stabilizing forces. So when it reaches the threshold value of 1, there is a landslide. Is made of different terms which are linked to the features of the soil, but there is one last term which is linked to suction stress, so it's linked to the water into the soil. There is a term, sigma, which depends actually on soil moisture and on rainfall through the infiltration rate. But here the message is that if we know the other terms, the first term and the second term can be calculated by knowing the soil parameters, basically. So if we have information, for instance, from remote sensing about soil moisture and rainfall, we can use this data into this equation, and we are able to estimate the factor of stability. And when it reaches the value of 1 or close to 1, there is likely a landslide, or however we are detecting landslide risk. So with this philosophy, what we have implemented is the implementation actually of the factor of stability in space, so spatially distributed in space, with 2 different data sets of rainfall from the project, MCM, which is a merging of rain gauges and radar, and another product developed within DTE. Together, as we said, no, it's important both rainfall and soil moisture. So together with 3 different versions of the soil moisture from Sentinel-1 at 1 kilometer daily. So basically 3 soil moisture products, a couple of products of rainfall, so 6 combinations in total. Here I'm just showing results for one event, but it's useful to understand the main features of the method. In these plots, in the red box, there is a rainfall event, so the occurrence of a landslide event, sorry. And you can see how we are looking at November, the year is 2019. When we detected the landslide, the soil water index, so basically the saturation of soil, was pretty high. And there was a rainfall event, second plot, and in fact in several points we detected a factor of stability close to 1, so landslide. It's important to note that, for instance, in October there was an higher rainfall but with lower soil moisture conditions and no landslide were detected. So this is the coupled importance of soil moisture and rainfall for landslides. Then on the right side there are tables summarizing basically the performances of the capability of detecting actually occurred landslides, because these predictions have been compared with actually occurred landslides. We can see, for instance, that MCM performs better than the other rainfall product. But apart from this, the message here is that you can implement this distributed in space and create a map of risk based on factor of stability as the one we were watching in the video. I'll try to be a bit faster here because I want to show you the platform. Basically, the second phase of the project was the evolution part. We have still all the components of the prototype, so the data cube, the modeling, the cloud-based platform, and so on. But here, the implementation was carried out over the whole Mediterranean basin. Also thanks to the synergy with another ESA project, which is for the DTE Hydrology project, whose aim was actually the project is still ongoing. The aim is to reconstruct the irrigation, the water cycle at the Mediterranean basin, over the whole Mediterranean basin scale. So what's important here is the cloud-based platform. This is the platform, there is the link, and as I said, this afternoon we will play a bit with it. Since we have not so much time, I will go directly to the details. What we have in the platform, we have the data cube, so we have the data. We have soil moisture, 1 kilometer daily. We have evapotranspiration, soil moisture 1 kilometer, 3 days, revisit time. We have evapotranspiration, 1 kilometer daily. We have rainfall. Rainfall is produced by merging several products developed in the project. However, we have 1 kilometer daily also for rainfall. We have snow. Snow data has not been developed inside the project, but we have basically taken sea snow product produced by Livens and others based on Sentinel-1. Then we have also other variables that comes from modeling, as for instance soil moisture, evapotranspiration, reverse discharge, through the hydrological model that integrates this data. But what can be done with the platform? This is what we will basically see this afternoon. I don't want to spoiler that much, but we can perform large-scale water balance assessment. So we have all the components of the cycle in the platform, and we can see the status, in terms of anomalies of all the fluxes and storages, and we can see if from some components we are in conditions of deficit or not. The same information can be visualized in another way as time series of anomalies, which of course are very useful for detecting drought event, as for instance summer 2017 there is clearly a deficit in precipitation, soil moisture, evaporation, and this can be clearly depicted by the data cube in the platform. But more interesting to me are the what-if scenarios. That is what I would like to show you in details this afternoon. Just a few words to introduce them. The first one is for flood risk assessment. Currently is implemented only over the Po Valley. We have 6 river stations in the Po Valley in which we can basically enter in this sense. We select the station and we say, okay, imagine that we have a mean soil moisture condition over the whole basin of 0.6 as here in the example, no? So basically the antecedent moisture conditions of the basin. And then there is in the previous 30 days the precipitation, the mean precipitation is of the accumulated value is 150. Okay, I select a river station and the system produces the hydrograph. It's a prediction in this sense, it's a scenario. So what we done, I will explain much more in detail this afternoon, but basically we ran several simulations with several initial conditions of soil moisture and precipitation, and we have created a database that is an ensemble of hydrographs of response in terms of discharge to several conditions of initial conditions of soil moisture and precipitation. When we enter here and we select our initial conditions, the system picks the closest scenario among all the scenarios that we have simulated, and basically tells us, look, with this condition, it's likely that this is happening. Or however, the closest scenarios among all that have been simulated that have happened is this one. So it's a kind of prediction in this sense. Similarly, for the sorry, here there is an error in the slide. This is what is scenario for water resources management. Again, here we have implemented over the Po Valley this tool. You basically provide the system with initial conditions of soil moisture and snow coverage and a 5 months forecast of precipitation and temperature. And for the next 5 months, the system produces a forecast of all the fluxes and storages involved in the cycle. Also, water uses for different components, agricultural, industrial, or civil. And basically, we can understand in this way with the water that we have available in the next 5 months and the use of water that we need, when we will have a deficit, if we will have a deficit, what is the magnitude of a deficit, or if we don't have a deficit, much better. But this tool, I think it's one of the most useful, no, in terms of the water resources management. As a final comment, in order to implement this tool, there is behind, of course, there is an hydrological model for which an irrigation scheme has been created properly for this application, and we have validated that model with our irrigation estimates over the Po Valley, also finding a good agreement. So this is also a good example of high connection between activities carried out in different ESA projects. Now, in the time series, there is in black the agricultural water used simulated by this model, which is at the basis of the tool, and in blue our satellite-based estimates at monthly scale. So, final remark, and I will finish now. The building of this kind of tool, so of a digital twin for water cycle, is feasible. There are challenges to be still addressed, mainly linked to 3 components, which are the need for real high spatiotemporal resolution Earth observation data, with several issues linked, so the uncertainties, the need for in situ networks for validation, also the perspective and the opportunities of the new satellite mission, and so on. We need modeling platforms able to integrate this data, as we already said. And we need to reproduce the complexity of human activities. We can do this with real high-resolution data, but also we need to incorporate these activities into models. So actually, the errors could be also in the opposite direction. It's actually a circular approach here. So each component is linked with the others. And that's it for this presentation. And this afternoon we will see also something about the platform, right, with hands-on. Thank you.